So we'll continue this lecture then talking about Reynolds Transport Theorem. So to give a little background, there are two basic reference frames from which we can work. We have the Eulerian reference frame, which has independent variables of x, y, and z, the spatial coordinates, and time, and we can track how particles move past these positions. So this is like the cell, the unit cell that we had the fluid flowing through. That cell was fixed in space, and we watch things go by it. The other type of reference frame that we can use is the Lagrangian reference frame, and that's supposed to say a certain blob of material is tracked, and it may deform. Now the Lagrangian system is very natural to use when we're formulating basic conservation laws. As we'll see at the end of this lecture, we're going to formulate the conservation of mass in the Lagrangian system. Then we'll be able to use the Reynolds Transport Theorem to get us to the Eulerian system. And the reason why we're often interested in the Eulerian system is that reference frame is often a lot more useful on solving some specific problems. So the Reynolds Transport Theorem is a means by which we can relate the two frames. Now this discussion is one that I'm going to present, and it's taken from the Fluid Mechanics book by Curry. It's several years old now, but you can probably still find a copy out there somewhere. This is going to get a little bit complicated, and I'll draw some figures in a moment. But we're going to start off by looking at the time derivative of a volume integral of some field quantity alpha that can change with time, and it's integrated over some volume. And this is in the evolving control volume. Now, by the definition of a derivative, we can take the limit as some small increment of time goes to 0. So I'll say delta t, the little delta, of this quantity in the bracket 1 over delta t for this quantity, an integral over the volume of t plus an increment delta t of the variable, the field variable alpha, evaluated at t plus delta t, minus, I need a dv right here, minus the integral at v of t with that spatial field variable alpha evaluated at time t, dv, close square bracket, close curly bracket. And that's just by the definition of a derivative. And here, again, alpha is any field variable. Right, so let's work with this right-hand side a little bit more and leave plenty of room. So we have the limit as delta t goes to 0. And I'm going to rewrite this slightly, and we'll find out why, but I'm going to add and subtract some like terms. The first bracket is going to have the first term in it. It's a volume integral at time t plus delta t, and integrating the field variable alpha t plus delta t over that volume. And now I am going to subtract a term that is at the volume at time t, but is of the field variable of alpha t plus delta t. Okay, so this is a new term that's not in the top expression, so if I'm subtracting it off here, I'm going to have to add it somewhere else. And I'm going to add it right now. I'm going to have this term 1 over delta t the volume integral of v of t, field variable alpha t plus delta t. I read over that volume. And now I'm going to subtract the v of t term, alpha of time t, dv, close square bracket, close curvy bracket. And that's perfectly fine that we do that. Now let's look at these in pieces. So the first one I'm not going to do anything with right now. I'm just going to rewrite it down. I'm going to have the limit as delta t goes to 0 of 1 over delta t square bracket. I'm going to rewrite it just a little bit differently looking. It's the volume of t plus delta t. If you notice, the integrand is fixed, so I'm going to write it this way: minus the volume at time t of this fixed integrand that's at time t plus delta t. And close square bracket, close curvy bracket. Okay, so this one, the integrand is fixed. But the volume is varied. Now the last term, we have 1 over delta t. We're taking the limit of that as that goes to 0. We have a fixed control volume, and we have an integral of alpha t plus delta t minus alpha t. Well, that is nothing more than an integral over that fixed volume. And then we have partial derivative of that field variable alpha with respect to time. Alright, so now we're going to take a look at that first term right here in a little bit more detail. Alright, so I have some blob of material. This is the volume at time t. And somewhere on here is a unit normal. And there's maybe some velocity. Call that u. Changing notation because we're using a different book. And then this volume is expanding. Okay, so maybe this is the volume at time t plus delta t. Right, now I'm going to try to copy both of these, and we're going to place one on top of the other. Let's see if I can do that. Probably should have made this one a little bit bigger. Tell you what, let me just do this. And now I'm going to copy this one. And I'm going to place it inside of here. So this is just kind of a way to show that this control volume is expanding over time, and its expansion goes in the direction of the unit normal. I'll draw a little area around it. And is propelled by that velocity u. Now, if we were to look at this difference between v and the v of t plus delta t surface, what we would have would be, if I can draw it, a little bit of surface from the original volume v, and then it's projected onto that volume of v t plus delta t. Now this surface that we have here, I'm going to call that delta S. And this distance is being driven by that velocity u. It's the amount of velocity in the direction of u, in the direction of the unit normal in, over a little bit of time, delta t. So the volume for this little bitty piece right here is given by this dimension times the surface area. It's given by u dot n delta t by delta s for the surface area. Alright, now that we have that, let's go back and take a look at our line that we have again. Okay, so that's where we have it so far. But now, with that other explanation of the dv, we can look at the time derivative of this volume of the integrated for the integrated field variable over that time. Then we can take the limit as delta t goes to 0 of an integral over the surface now of alpha t plus delta t dv, which is u dot n delta t ds, and we have the delta t right here, but this will actually cancel out with this term. And we have plus this integral v of t, partial of alpha with respect to time, dv. So let me write this one more time. In the limit, since that delta t has gone away, it's algebraically canceled. We're going to have an integral over the surface at time t of the field variable. We put in the delta t goes to 0 of alpha of t u dot n ds. Then we have the plus the volume integral of the partial derivative of alpha with respect to t dv. All right, now let's look at this term in a little bit more detail. We have a surface integral of alpha of t of u dot nds, we can convert that into a volume integral using the divergence theorem. Okay, so now we have del dot alpha u dv. Alright, now let's start to put this together. Let me make a little bit more room. So now we have both of these terms on the right hand side and on the left hand side as well as volume integrals over the same volume. So I'm going to rewrite this one more time. D by dt of v of t of the field variable alpha of time is equal to a volume integral of, I'm going to lead off with the partial derivative term, partial derivative of alpha with respect to time plus del dot alpha u dv. Or we can write it the other way. It's a volume integral if we use our subscript notation. Partial of alpha with respect to time plus partial with respect to xk of alpha uk dv. Alright, so what does this mean? Over here on the left-hand side is the change in some quantity in a volume. This is the Lagrangian side. Okay, so this is the change in some field with time in a control volume. And over here, this is very much tied to our coordinate system, like our XYZ coordinate system. Over here is the spatial or the Eulerian description. So now with Reynolds Transport Theorem, we have a way to relate the Lagrangian in the Eulerian reference configuration. Let's see what happens when we think of the concept of the conservation of mass in a volume. Now I mentioned previously that we've already done the conservation of mass, and that was part of the Eulerian continuity equation. I've always found that to be less than satisfactory as a way to formulate the conservation of mass. But the Lagrangian formulation is very intuitive, and it's very nice. Well, if we have a control volume, if we integrate the density over that control volume, then we have the mass that's inside that control volume. And if we are conserving mass, what that means is the time derivative of that mass is equal to 0. Well, by the Reynolds Transport Theorem, we can rewrite this integral as integral over the volume of partial derivative of the density with respect to time plus the partial derivative, the density times the velocity. Now I'm using vi now with respect to position, coordinate xi. And that is also equal to 0. And since we have an arbitrary control volume, then the integrand has to be 0 if that whole integral is equal to 0. And out of this very simple idea of the conservation of mass from the Lagrangian point of view. Using the Reynolds Transport Theorem, if that makes sense, then what we have is the partial derivative of density with respect to time plus the partial derivative of rho vi with respect to xi equal to 0. We have the Eulerian continuity equation. Like I said, somehow I just find the Lagrangian formulation just so much more easy to grasp, very easy to write down. Conservation of mass means that the mass doesn't change over time. Reynolds Transport Theorem, now we have the Eulerian continuity equation. Well, let's investigate this idea of mass and a control volume just a little bit more. So we can get some insight by examining what happens from an undeformed to a deformed configuration in a Lagrangian reference frame. So we have some volume here. Our undeformed region V has some density, and the mass inside of that is going to be the volume integral of the density over that volume. And this body distorts and deforms. Maybe it gets a little bit bigger. We have some new region, some new volume, script V, and the mass inside of it is the new density. The density is going to change. So that new density, rho star, integrated over that new volume region. So we can write down the density changes from rho to rho star, keeping the same mass. So over here on the undeformed region, we can express this in terms of dx, dy, dz, are infinitesimals for this volume element V. Over here on this side, if the masses are the same, then we can have an integral over the script volume of the new density over its infinitesimals. In the deformed region, we call them dxi1, dxi2, and dxi3. Now here's where we can bring in some things all the way back from several lectures ago, when we recall that there's a one-to-one transformation between the infinitesimals in the undeformed region and in the deformed region. If we have a continuous deformation or an admissible deformation, then the xi sub I can be written as functions of x, y, and z, and the d xi I with respect to spatial position dxj and the d xi I can be written as the partial derivative of xi I with respect to xj dxj in the set of infinitesimals dxi1, dxi2, dxi3 can be written as the Jacobian times dx1, dx2, and dx3, or dx, dy, dz, where the Jacobian is the determinant formed by the matrix of components of these partial derivatives dxi I with respect to xj. So let's see what that does for us. Then the volume integral over the original volume of rho dv we said was equal to, if mass is conserved, a volume integral over the new volume of the new density, which we can express in terms of the original volume. original reference configuration. And since these two terms are over the same volume, we can group them together. Since the volume of integration is arbitrary, if the integral goes to 0, the integrand must go to 0. Then the density is equal to the Jacobian times the new density. Or we can even say that the Jacobian can be used to find the density ratio of these two materials. This is known as the Lagrangian continuity equation. Okay, so the Jacobian is a measure of the spatial distortion, and it can be found by taking the ratio of the density in the undeformed configuration to the density in the deformed configuration. So there's a couple ways to interpret this. Let me write it down, then I'll say it. So the density has to change if the volume of the region changes, or conversely, the relative density change is related to the spatial distortion. Now, we can think of a place where density goes to infinity, where we have a severe amount of spatial distortion, and basically that's what you get when you apply continuum mechanics to space, as Einstein did in his general theory of relativity. When you have an area, a region of space where the distortion is so great, where you have basically an infinite density, then you have the continuum breaking down, or the black hole. So that's kind of an interesting perspective on it. And it all kind of goes back to continuum mechanics. And that's something that I would like to learn more about, and I find pretty interesting. Well, we had some discussion on the conservation of mass and continuity equations. We had this very useful Lagrangian continuity equation and the Reynolds Transport Theorem and the Eulerian description of the continuity equation. And everything gets kind of tied together. Now we still have some conservation laws to talk about. Rather than taking them one at a time in this section, it's kind of natural to talk about the conservation of mass now while we've just finished talking about strains and distortions of the body. But now we're going to start on stress next, and then we'll also include a couple of more conservation laws, conservation of linear and angular momentum.